So, rational equations, and I'm on the front of that paper that you grabbed on your way in. They are equations that involve fractions. So I'm just being honest with you. They are a little more involved. There's things that happen on a rational equation that may have never happened before, that you may have never seen before. But I want to introduce some of them to you through this somewhat fun, but also realistic situation that is kind of presented in this box at the top here. So we have this fellow named Hershey, kind of fitting that would be his name. Now, he missed school for 6 months, but when he returned, his math class wanted to give him a present. They gave him 36 chocolates. Okay, so he's got 36 chocolates, and he's basically trying to figure out, do I want to eat them all, or do I want to share them? And of course, what's going to happen in those scenarios? This can actually be modeled with this very simple but realistic equation. This equation you see here, y equals 36 over x. Now, as you look at this equation, it's obviously a fraction, but it's really just a simple division problem, because if x is going to be the number of students that basically get the candy, then I'll divide by x. And then y will be the total number of pieces that everybody gets. And let's take a look at a little bit of a pattern that might occur with this scenario. Oh, I almost forgot. It's a good time to fill in the blank here that this is a rational equation. This is a rational equation. Okay, the word rational is kind of fancy, but in math class that just means it's a fraction. Okay, now remember what's going on here. You've got 36 pieces of candy, and well, if one student's going to get the candy, I guess that would be probably the guy that it was given to, then I'm going to divide by 1. And obviously, if you take 36 and divide it by 1, you're going to get 36. That means he's going to get all the piece of candy. What if I'm going to give it to 2 people? That's probably going to be himself and a friend. Well, 36 divided by 2, obviously now everybody gets 18 pieces of candy. Now, it's supposed to be kind of an easy math problem. You don't need me to tell you that 36 divided by 3 is 12, but I do want you to realize that that means that 3 students are each going to get 12 pieces of candy. You want to take a moment and just figure out what else people get? You're dividing by 4, by 6, and so forth and so on. It should be pretty clear to you that as more and more people get the candy, that they receive less and less pieces of candy. And we'll talk about that basic idea in just a moment. Now, maybe when you got down to the number 72, you kind of wondered, wait, what's going on here? Well, first of all, that's 72 people that are going to get candy. Can that happen? Yeah. There's a knife. We could cut the chocolate in half. So if 72 people are going to get the candy, everybody gets a half a piece. So yeah, that can happen. What if I take this a little bit to the extreme, though? What if 1,000 people are going to be given candy, like everybody that's in school today? Now, on a practical side, you might say, that's not going to be able to happen. Well, you're right. I mean, on a practical side, you're not going to probably have enough. It's not going to be a big enough piece to give everybody a little morsel. But mathematically, what number am I approaching? What number am I approaching if 1,000 people are going to get a piece of candy? Mathematically, I'm approaching 0. Now, what you want to understand here is that it's not equal to 0 because there's still a morsel. But mathematically, we have an argument that if we're going to give the candy to 1,000 people, that the amount of candy they're getting is getting closer and closer to 0. But it's not equal to 0. Okay, we're going to talk about that in a second, basically what that has to do with the graph, the idea of approaching 0. Let's go up to the top. You might notice that I had a spot there that was empty. What if 0 people get the candy? Now, again, practically speaking, I don't know, maybe this means that the candy just gets thrown away because everybody's arguing or something, so we just throw it away. But mathematically, what happens if you divide by 0? What if you take 36 and divide it by 0? Well, mathematically, that can't happen because you can't divide by 0. So we say that it's undefined. We're also going to talk about what that means in a moment on the graph. Okay, so just kind of want you to be wondering what's going to happen at the sort of the ends of the graph. What happens if I have this 1,000? And then what happens with this undefined? Before we get to the ends of the graph, though, let's just graph the points. Okay, now I'm sure you've plotted points before when you were trying to investigate an equation. That's kind of what's going on here. We're just going to plot the point 136. Now, notice the scale that I'm using here goes by ones, but I tried to label some of the places so you don't have to like keep starting over with your counting. So just try to find these points. Try to find 218. 218 is going to be right there. And go ahead, take a moment, plot your points. Try not to get a headache with all the lines and counting. Hopefully your graph looks similar to this. I would say that we're unable to graph 72. That's going to be over in the margin, so don't bother graphing 72. But you should be able to get most of the rest of those points and see this type of shape. Now remember, when it comes to graphing an equation, it's more than just 10 points. The equation is actually the entire line. Do you feel confident that you can connect these dots in the basic shape that these points are making? Well, I'll try my best to connect them. It's just basically a smooth line, as smooth as you can make it. I'm going to kind of stop my line because what we want to do is we want to talk about what's happening at the end of the graph. So if you just want to stop your line, in other words, let's wait for a moment and we're going to talk about the end of the graph. Now, probably one of the main reasons we're doing this little intro is because of the end of the graph. You say, what do you mean the end of the graph? Well, I didn't really graph 72, but if I was going to graph 72, I know that my graph would start getting closer and closer to the x-axis. If I was going to graph 1,000, again, I know I can't graph 1,000, but if I was going to, my graph would continue to get closer and closer to the x-axis. It would kind of keep lowering itself. Well, the reason that is happening is because of this idea of getting closer and closer to 0. In fact, y equals 0, the line y equals 0, which I am trying to show by this dashed blue line, is a special feature on this graph. Now make sure you follow this. This is one of the main reasons we're doing this. The line y equals 0 is like a boundary. It's a boundary that is known as an asymptote. In fact, specifically, it's a horizontal asymptote. It's this idea that if I'm going to give the chocolate to 1,000 kids, there's still going to be something to give them. It's not going to equal 0. In fact, if I give the chocolate to 5,000 kids, and you get the idea that we're just going to keep getting closer and closer to 0, which is known as an asymptote, which is a boundary or a line that I'll approach but never cross. And mathematically, we can make somewhat of a fancy statement, but I want to show it to you. We can say as x approaches infinity, in other words, as the number of students that get the chocolate gets very large, the y value is going to approach 0. But keep in mind, it's not going to equal 0. And that is known as a horizontal asymptote. Did you draw your graph so that it kind of goes out to the right? Did you draw your graph as if it's trying to go to infinity? And it gets closer and closer to that blue line. Now, you may not be surprised to hear that we have something similar happening, but this time it's happening at x equals 0. Now, x equals 0, focus on x equaling 0, is another boundary, but it's a vertical boundary. And I'm going to do my best to denote that with this purple dashed line. Can you see that purple line? I drew a purple dashed line at x equals 0. And in a similar fashion, that is saying that as I get closer and closer to x equaling 0, my graph is going to continue to go up. Again, it's actually going to continue to go up. And I have no choice but to try to draw that kind of on top of the paragraph. Okay, but what I really want you to understand is that a vertical asymptote, in the same way, is a boundary that your graph is not going to be able to cross. That's because as x gets closer to 0, that means the number of students that are getting the chocolate, the y value, that means the number of chocolates they get, is actually going to get very large. It's going to go to infinity. It's sort of the reverse statement, but it's still an asymptote. Again, it's known as a vertical asymptote. Okay, now the graph that we drew is an inverse relationship. And as you probably noticed from the very beginning, as one quantity goes up, the other quantity goes down. Basically, the number of students that get the chocolate keeps decreasing. But when you have an inverse relationship like this, you also end up with, again, with these asymptotes. Okay, now there's a lot more to say about asymptotes. That's why we have next week. But I want to investigate briefly negative numbers. Even though they don't make sense for Hershey's chocolate, they do make sense mathematically. If I want to divide by or plug in -4, sure, you can divide by -4, you get -9. If I want to plug in -6, sure. And so the point here is that negative numbers mathematically can also be part of our graph. Well, you take a moment and graph them. The only spot to do it is down here in the lower left corner. That's why there's only a few numbers that we can graph. I think -4, -9 is just off the graph, but I would still try to put a dot down there. -6, -6. You can definitely get that one on. Hopefully you're able to see these 4 points that kind of look like a little bit of an arch or a little bit of an elbow. when you connect the dots, you can take a little bit of liberty to extend the graph as I'm showing here in red. When you connect the dots, I actually want you to realize that the asymptotes are still doing their thing. That is, the graph is going to continue to get closer and closer to each of those asymptotes, but still never touch. We just don't have a lot of space to draw the graph really big. Now you see what's known as branches. Branches. In fact, the graph that we drew has 2 branches. This is technical talk for the type of graph that we have. We have like a positive branch. We have like a negative branch. And again, a lot of these things I just kind of want you to hear so that when we get into it next week, it's not the first time. On the back, there is, well, first of all, it's always funny to see your reaction. But yes, on the back, there is another graph. There's actually a little bit more going on with this graph. It's supposed to be a little bit more interesting. I don't want you to get overwhelmed by a graph paper, but it can look overwhelming. The scale is actually going by 1/4 because you're going to end up with some decimals. Okay, and if you're going to graph some decimals, I wanted you to be able to be as precise as possible. Listen, when you're graphing some of these points, I wouldn't take any more than 10 seconds to estimate its location. I don't want you to get so bogged down that you're like trying to get the exact spot, because some of them you're not going to be able to. But I would like you to be able to complete the table of values so that you can get a graph, so that you can see some asymptotes and continue to kind of introduce yourself to this idea. Okay, now I'm going to just kind of provide a little guidance on how to get some of these numbers on your calculator. This is kind of one of those things where you need to say, okay, Ms. Naylor, I'm going to try this. If you don't try it, you're not going to know if you're basically using your calculator correctly. Now, even though I did give you some of the answers, if you look at how I'm suggesting that you plug in 100, you have to go heavy on the parentheses. Okay, I'm serious. You just basically have to type this in with parentheses around the numerator and around the denominator. And if you're willing to give this a try, even though I already wrote the answer down, you can check if you're typing it in right. I do recommend that you just type the whole thing in. And you need to put parentheses around the numerator and the denominator. And negative 100. So go heavy on the parentheses. Okay, again, I provided some of the numbers so that you can say, okay, I'm on the right track. You'll notice that I rounded it to 2 decimal places. You should be able to graph it pretty closely to a decimal or 2. Okay, now in a minute here, we're going to shift gears to that mini check that I was talking about, but I just wanted to get you started on the back and hopefully interested in trying to fill out this table. You do have to fill out the whole table. I don't really care if you kind of do it with a partner. Maybe you share some numbers. What I really care about is that you try to graph your table. Okay, now when you do graph the table, maybe it's going to be after class, maybe it's going to be sometime this weekend. There's going to be some asymptotes, and it's a little bit more complicated than the one I did on the front. If you look at the bottom, there's a tiny URL. Check it out, but don't check it out too soon. Okay, don't check out the tiny URL too soon. I want you to see if you can introduce yourself to this without completely being given the answer.